dark matter and the strangeness of time. Far out beyond the reach of any light we have ever sent, beyond the last galaxy we can see, and beyond the faint background glow that whispers of the universe's first morning, is something we cannot find. It is everywhere. It outweighs every star, planet, and grain of dust by a factor of 5. It moves through us as we sit here. It moved through us yesterday. It will move through us tomorrow. We will never feel it. Tonight, we will drift through what little we know of this hidden thing. There is no hurry. There is nothing here that needs to be solved or remembered. The universe has waited a long time to be understood. It can wait a little longer. We will speak of dark matter. We will speak of what it might be and what it is not. We will speak of how it relates to time differently from ordinary matter. Dark matter does not cool, does not radiate, and does not age as stars age. We will speak of theories that imagine it decaying slowly across the cosmos. Other theories imagine it as a vast wave, oscillating so slowly that a galaxy is barely a heartbeat. None of these theories has been proven. None has been ruled out. The truth, whatever it is patient. It has been patient for 13 billion years. The astronomers who first stumbled on the existence of dark matter did not understand what they were seeing. They thought they were studying galaxies. They were studying galaxies, in a sense. But what they were really doing was finding the edges of our knowledge, the places where the maps grow blank and the math stops working. They found that the universe is mostly something we cannot see. And then, very slowly, over the course of nearly a century, they tried to figure out what that something might be. So settle in. There is no urgency to any of this. The dark matter that surrounds us has been here for almost the entire age of the cosmos. It will still be here when we wake. Let the mind drift, and the words drift with it, and we will go slowly through the dark. It begins, in most tellings, with a man named Fritz Zwicky. He was Swiss, born in Bulgaria, raised in Switzerland, transplanted later to the dusty hills of Pasadena, where he spent the better part of his working life at the California Institute of Technology. He was brilliant, irascible, sometimes intolerable to his colleagues, and he saw things in the sky that others were not yet ready to see. He invented several of the central ideas of 20th century astrophysics. He was the first, with his collaborator Walter Baade, to suggest that exploding stars called supernovae left behind dense remnants made of neutrons, the objects we now call neutron stars, decades before the first one was observed. He was, by most measures, a man ahead of his time. He was also, by most measures, a man who knew it and who said so often, and who did not endear himself thereby to his peers. In 1933, working at Caltech, he turned his attention to a great swarm of galaxies known as the Coma Cluster. The Coma Cluster is one of the richest collections of galaxies within our observable horizon, more than 1,000 galaxies bound together by gravity, drifting through space at a distance of roughly 300 million light-years from Earth. It sits in the direction of the constellation Coma Berenices, Berenice's hair, named for an Egyptian queen who sacrificed her tresses to the gods. The galaxies in the cluster appear, in long-exposure photographs, as countless small smudges of light, each one a great wheel of stars in its own right, all gathered together by their mutual gravity. Zwicky wanted to weigh it. The method he used was old, elegant, and reliable. If you know how fast the members of a cluster are moving, and you know how big the cluster is, you can calculate how much mass the cluster must contain in order to hold itself together. The relationship is captured by something called the virial theorem, which connects the average kinetic energy of a bound system to its average potential energy. Stars in a galaxy, galaxies in a cluster, planets around a sun. All of them obey the same essential relationship. Gravity must balance motion. Otherwise, the system flies apart. So Zwicky measured. He looked at the redshifts of the galaxies in Coma, at how their light had been stretched as they moved, and he calculated their velocities. He found that the galaxies were moving very quickly. Very quickly. Differences of more than 2,000 kilometers per second between some of them, when measured against the cluster's average motion. By his rough early estimates, the cluster would need to contain something like 400 times more mass than the visible stars could account for in order to hold its galaxies in their orbits. Otherwise, the cluster should have come apart long ago. It should have flown to pieces, scattered across the deep, leaving no trace of its former gathering. But it had not. It was still there, still bound, still holding together, and so something had to be exerting the gravity needed to hold it. He used the German phrase Dunkelmaterei, dark matter, unseen matter, mass that exerted gravity but emitted no light. He suggested, with some hesitation, that there might be a great deal of it. He wrote in a passage that historians of science still return to, that if his result were confirmed, then it would mean the universe contained vastly more dark matter than luminous matter. The phrasing was almost casual. It was the kind of remark a careful scientist might make in passing, knowing that more work would be needed before the conclusion could be drawn firmly. His paper was published in a Swiss physics journal, Helvetica Physica Acta, in 1933, and it was, in the way of such things, largely ignored. Zwicky was difficult. The result was strange. The astronomical community was busy with other questions. Hubble had only recently established that the universe was expanding. The basic structure of galaxies was still being worked out. Stellar physics was in flux. There were many things to think about, and a Swiss physicist's claim about hidden mass in a distant cluster did not seem, at the time, to be the most pressing. For decades, the missing mass of the Coma Cluster sat quietly in the literature, a curiosity, a footnote, an unresolved oddity. Other astronomers found similar oddities elsewhere. In 1936, Sinclair Smith looked at the Virgo cluster and found something comparable. The mass implied by the motion of the galaxies was far greater than the mass implied by their light. Smith calculated an average galaxy mass that was hundreds of times larger than Edwin Hubble's accepted estimate. He, too, considered this a problem. He, too, was unsure what to make of it. These results, like Zwicky's, sat in the journals, half forgotten, waiting for someone to take them seriously. In 1937, Zwicky returned to the question. He published a longer English-language paper in the Astrophysical Journal, refining and extending his analysis. He considered several different methods for weighing the cluster, and each gave a similar answer. The mass was too large. The light was too dim. Something invisible was doing most of the work. He laid out the case carefully, and the case was strong. But again, the community was not ready. The mid-20th century was a time of many other discoveries: the structure of the atom, the unfolding of stellar evolution. The first hints of the cosmic microwave background were discovered in 1965. Dark matter, as a concept, was not yet ripe. Other astronomers, in those quiet decades, made discoveries that pointed in the same direction without being immediately recognized. As early as 1939, Horace Babcock measured the rotation of the Andromeda galaxy and found that its outer regions were moving faster than expected. He explained this, at the time, by suggesting that the outer parts of the galaxy must be richer in dim stars, or perhaps dust. In the 1950s, observations made with radio telescopes tracking the 21-centimeter line of neutral hydrogen, began to show flat rotation curves in other galaxies. Morton Roberts, in the late 1960s, reported on the rotation of Andromeda using radio data, and he found that the rotation curve remained essentially flat far beyond the bright disk. He suggested, cautiously, that the outer regions of Andromeda might contain a great many dim red dwarf stars. The idea of dark matter, as something separate from ordinary stars, had not yet crystallized. The slow rediscovery of the problem came in the late 1960s and through the 1970s, and it came largely through the work of an American astronomer named Vera Rubin. She did not set out to discover dark matter. She set out to study how galaxies rotate. Vera Rubin was, in many ways, an unlikely figure to overturn the standard picture of the universe. She had been told, as an undergraduate, that Princeton's astronomy program did not accept women. She had been the only astronomy major in her class at Vassar. She had done her doctoral work under George Gamow at Georgetown, choosing a part-time program because she had a young family to look after. Her early career was made of small, careful contributions, none of them flashy, all of them solid. She avoided controversy. She had been burned early on by a paper she wrote suggesting that galaxies might be moving in coordinated patterns, a result that turned out to be premature, and she did not want to be in that position again. So when she turned, in the late 1960s, to the rotation of galaxies, she chose the question because it seemed safe. It seemed like a problem that would yield clean, reliable data. She and her collaborator, Kent Ford, had access to a new kind of spectrograph that Ford himself had built, an instrument sensitive enough to measure the velocities of stars and gas at the faint, outer edges of distant galaxies. The new device used an image tube to amplify faint starlight by a factor of 10 or more, reducing the exposure times that had previously made such observations nearly impossible. They began with Andromeda, our nearest large neighbor, the great spiral some 2.5 million light-years away, the only galaxy outside our own that the unaided eye can see from a dark site on Earth. The expectation when they began was this: in the solar system, the planets near the Sun move quickly, and the planets far from the Sun move slowly. Mercury hurries around the Sun in 88 days. The Earth takes a year. Neptune takes nearly 165. This is because most of the mass of the system is concentrated at the center, in the Sun itself. Out at the edges, gravity weakens and orbital speeds decrease. The same logic, applied to a galaxy, suggested that stars near the visible center should move quickly, and stars in the dim outskirts should move more slowly. Rubin and Ford expected to see the rotation curve slope downward at large radii, just as Newtonian gravity demands when most of the mass sits at the center of a system. They did not. The stars at the edges of Andromeda were moving just as fast as the stars near the center. The rotation curve was flat. It stayed flat all the way out as far as they could measure. They thought at first that there must be some error in the data, some misunderstanding of the instrument, some subtle effect they had not accounted for. They checked. They rechecked. The data stood. They moved to other galaxies. The same pattern. Rubin later recalled in interviews that the early observations were puzzling. She did not immediately understand what she was seeing. It took months of staring at the printouts before the meaning began to take shape in her mind. One day, she remembered, she sat down with a piece of paper and a pencil and tried to sketch out what the implications were. If the rotation curves were flat, she realized, then the mass of each galaxy could not be concentrated at the visible center. It had to be spread out. It had to extend far beyond the bright disk. It had to fill a large halo, much larger than the galaxy itself, in order to keep the outer stars moving at the speeds she was measuring. She and Ford surveyed dozens of spiral galaxies, then dozens more. The result was the same for everyone. The rotation curves did not fall. The outer stars moved as if there were a great deal of mass beyond them, pulling them along, holding them in their orbits. Between 1976 and 1986, Rubin and her collaborators published nearly 50 papers on the topic. In 1980, a particularly influential paper appeared in the Astrophysical Journal, presenting the rotation curves of 21 spiral galaxies, spanning a wide range of sizes and luminosities. They were all flat. There was no exception. The explanation that survived, after years of debate and skepticism, was the explanation Zwicky had hinted at 4 decades earlier. Each galaxy was embedded in a vast spherical halo of invisible matter. The halo extended well beyond the bright edge of the visible disk. It outweighed the visible stars and gas by a large margin. It was everywhere, and we couldn't see it anywhere. Rubin herself was cautious about the term dark matter. She preferred to let the data speak. In her early publications, she did not always use the phrase, and she sometimes pointed out that her observations did not, by themselves, rule out other explanations, such as a modification of gravity at low accelerations. She was careful in a way that the field rewarded her slowly. But by the early 1980s, even her most skeptical colleagues had come around. The flat rotation curves had been confirmed by radio telescopes, by independent groups, by every method anyone could think of to check them. Something was holding the galaxies together, something invisible, something that had been there all along, unnoticed, unweighed, threading through every galaxy in the sky. Rubin lived until 2016. She received many honors. The Vera Rubin Observatory in Chile, which began releasing its first images in 2025, was named for her. But the Nobel Prize, which many felt she deserved, never came, in part because the prize is rarely given for discoveries that have not been directly confirmed in a laboratory. And dark matter has not, to this day, been caught in any instrument we have built. She herself asked about the omission, tended to deflect the question, saying simply that she had had a long and good career, and that the joy of the work had been its own reward. She continued observing well into her later years, gentle in temperament, generous to younger astronomers, modest about her own role in the story. The dark matter she helped to reveal would, she sometimes said, take generations more to understand. The discovery did not feel triumphant. There was no single moment of revelation. There was only the gradual accumulation of measurements, the slow turning of opinion, the recognition that the universe was much stranger than anyone had supposed. Most of it by mass was something we could not name. Most of it by mass was something that did nothing visible. Most of it by mass was something whose presence had to be inferred from the dance of the things we could see. The numbers, when they came, were unsettling in their precision. By the time the Planck Space Telescope finished its careful survey of the oldest light in the cosmos, the cosmic microwave background, the proportions had been fixed with a clarity that earlier astronomers could only have dreamed of. The universe is roughly 5% ordinary matter, the stuff of stars and planets and bodies and breath. It is roughly 27% dark matter, this invisible thing whose presence we infer but never see. The rest, about 68%, is something called dark energy, which is a separate mystery for a separate night. The figures have been refined many times. They will be refined again, but the overall picture is steady. 5%, 27%, 68%. The visible is the smallest part. The visible is the foam on a very deep sea. 5% is everything we have ever touched. 27% is everything we cannot. And we have spent the better part of a century trying to figure out what that 27% might be. There is a thought worth sitting with here before we move on. The astronomers who pursued this question for decades did so without ever holding the substance they were studying. They built their case the way one builds a case for a wind by watching the leaves move. They could not gather samples of dark matter. They could not weigh it on a scale. They could not see it, hear it, touch it, photograph it, taste it, or smell it. They could only watch the things it pulled on and infer from the pull. The whole edifice of modern cosmology now rests on a substance no one has ever directly perceived. It is a remarkable act of patience and trust in the consistency of the universe that we have built so much on so little. Let the room grow quieter if it wishes. The night is long. The first task, when the missing mass had become clear, was to rule things out, to say what dark matter is not. This is slow work, and it is often discouraging, and it has taken decades. But it has narrowed the possibilities considerably, and the narrowing itself is a form of progress. The most natural suggestion, when the problem first became clear, was that the missing mass was simply ordinary matter that happened to be dark. There are many things in a galaxy that do not shine brightly. Cold gas clouds, dust, dim, low-mass stars, burnt-out stellar remnants, brown dwarfs, which are objects too small to ignite the fusion that makes a star, drift through space at temperatures cooler than the surface of a candle. Old white dwarfs, neutron stars, stellar mass black holes. Astronomers gave this category of candidates a name. They called them machos, an acronym for massive astrophysical compact halo objects. The name was a deliberate play on WIMPs, weakly interacting massive particles, which were the other leading candidate at the time. There was, in the 1990s, a certain rivalry between the camps, with the macho advocates pointing out that there was no need to invoke new physics if the missing mass could be explained by ordinary objects, and the WIMP advocates pointing out that new physics might be exactly what the universe was trying to tell us about. The hope was that if you added up enough of these dim, unobtrusive bodies, you could account for the missing mass without invoking anything fundamentally new. Brown dwarfs, in particular, seemed promising. They are abundant. They are hard to see. They have most of the properties one would want, except that no one had ever counted enough of them to make up the mass deficit. For a while, machos seemed promising. In the 1990s, several large-scale surveys looked for them by watching for gravitational microlensing events, brief flickers of brightness in distant stars caused by a dark object passing in front of them. The technique is elegant. When a massive object passes between us and a more distant star, its gravity acts as a kind of lens, briefly focusing the starlight and making it appear brighter for a few hours or days before fading again. If the halo of our own galaxy were full of these dim bodies, the surveys should have found many such events. They found some. They did not find nearly enough. The Macho Project, the Eros collaboration, the Ogle survey, all looking toward the Magellanic Clouds and the galactic center, all painstakingly counting microlensing events, all concluding that compact dark bodies could make up only a small fraction of the missing mass. Whatever dark matter is, it cannot be mostly made of conventional objects like these. There are simply not enough of them. There was another reason, deeper and more compelling, why dark matter could not be ordinary matter in some hidden form. The reason has to do with the first few minutes after the Big Bang, an epoch known as Big Bang nucleosynthesis. In those minutes, when the universe was a few hundred seconds old and the temperature was around 1 billion degrees, the universe was hot enough and dense enough to forge the first atomic nuclei: hydrogen, helium, and a trace of lithium. The exact proportions of these light elements depend, very sensitively, on how much ordinary matter was present at the time. A universe with more ordinary matter would have produced different ratios of helium to hydrogen, different traces of deuterium, and different abundances of lithium. The relationship is well understood. The calculation has been done many times. By measuring the cosmic abundances of helium and deuterium in old stars and in distant gas clouds, astronomers can calculate, with considerable precision, how much ordinary matter the universe contains. The answer they get is the same 5% that the Planck satellite would later measure from a completely independent direction, by studying the patterns in the cosmic microwave background. The two answers agree. There is room in the universe for only so much ordinary matter, and the missing 27% is something else. It must be. The numbers do not allow for anything else. So dark matter is not gas. It is not dust. It is not dim stars or quiet planets, or the slow remnants of long-dead suns. It is something that the early universe did not make in the way it made the rest of us. It is something that existed already, before the elements were forged, before the first photons were freed to travel through transparent space, before there were any of the structures we know. For a long time, the leading candidate was a hypothetical particle called the WIMP, a weakly interacting massive particle. The idea was elegant. If there existed a kind of particle that had mass, perhaps 100 times the mass of a proton, perhaps more, and that interacted with ordinary matter only through gravity and the weak nuclear force, it would behave exactly as dark matter is observed to behave. It would clump under its own gravity. It would not radiate light. It would pass through ordinary matter almost without effect. Theoretical physicists had reasons, derived from particle physics, to expect such particles to exist. Supersymmetric extensions of the standard model of particle physics, in particular, predicted a lightest, stable, supersymmetric particle that would naturally have the right properties to be dark matter. The convergence between cosmological necessity and theoretical expectation was striking. People called it the WIMP miracle. The numbers seemed to line up too well to be a coincidence. Experiments were built, deep underground, to try to catch one as it drifted through. The experiments are remarkable in their patience. They sit far below the surface of the Earth, in mines and tunnels, shielded by miles of rock from the constant rain of cosmic rays that would otherwise confound any sensitive detector. There is one in a former gold mine in South Dakota, called the Sanford Underground Research Facility, where the Lux experiment ran for several years and was later succeeded by an even larger detector. There is one in a tunnel under the Gran Sasso Mountain in central Italy, where the xenon experiments have been growing larger and more sensitive with each generation. There are others in Canada, in China, in Australia. The detectors are similar in principle. Inside each one is a large tank of liquid, usually xenon or argon, cooled to nearly the temperature of liquid nitrogen. The tank is watched by an array of sensitive light detectors. If a dark matter particle were to pass through the tank and bump into a xenon nucleus, it would deposit a tiny amount of energy. The recoiling nucleus would briefly produce a flash of light and a small puff of free electrons. The detectors would register both signals. The energy would be measured. The location of the interaction would be reconstructed. If enough such events occurred with the right energies in the right pattern, the experimenters would have a signal. For years, the detectors have been running. For years, the researchers have been waiting. The signals have not come. The large underground xenon experiment ran from 2012 to 2016 with progressively larger fiducial masses and found nothing consistent with a WIMP. The xenon experiments in Italy in successive generations have looked deeper still into smaller and smaller possible interaction cross-sections and have found nothing. The simplest, most natural versions of the WIMP hypothesis have been ruled out, one by one. The supersymmetric particles that were supposed to be lurking just out of reach have not appeared, neither in the detectors underground nor in the high-energy collisions at the Large Hadron Collider in Geneva. The WIMP miracle has begun to seem less miraculous. Some physicists have begun to use the phrase nightmare scenario, by which they mean a universe in which the WIMPs are real, but lie just beyond the reach of any experiment we are ever able to build. The WIMP, if it exists, must be lighter than expected, or rarer than expected, or stranger than expected. With each year that passes without a detection, the simple version of the WIMP idea grows a little quieter, a little less compelling. It is not yet ruled out, but it is no longer the confident answer that it once seemed. There are other candidates. There is the axion, a particle so light that it would behave almost like a wave, spread out across an entire galaxy. There are primordial black holes, objects that might have formed in the first instant after the Big Bang, before any stars existed, and that might drift invisibly between the galaxies. There are sterile neutrinos, hypothetical relatives of the ordinary neutrinos that already pass through us by the trillions every second. There are more exotic things, hidden sectors, dark photons, mirror matter, ideas that bloom and fade in the theoretical literature. The axion is worth lingering on, because it has a peculiar origin and a strange beauty. The axion was not originally proposed as a dark matter candidate at all. It was proposed in the late 1970s as a solution to a different problem in physics, called the strong CP problem, which has to do with why the strong nuclear force does not violate certain symmetries that, in principle, it could. The American physicists Roberto Pexi and Helen Quinn proposed a new symmetry in 1977, and Steven Weinberg and Frank Wilczek showed shortly after that this symmetry, if broken, would imply the existence of a new very light particle. Wilczek named it the axion after a brand of laundry detergent because it would, he said, clean up the strong CP problem. The axion would have to be extremely light by the standards of particle physics, perhaps a millionth of the mass of an electron, perhaps even lighter. So light that it would not behave like a discrete particle in the usual sense, but rather like a slow wave filling all of space. Within a few years of its proposal, physicists realized that if the axion existed, the early universe would have made enormous numbers of them. And those axions would now be drifting through the cosmos as a cold, slow, coherent field. The axion, originally invented to solve a different problem, turned out to be a natural dark matter candidate. Experiments have been built to look for it. The most well-known is the Axion Dark Matter Experiment, or ADMX, located at the University of Washington in Seattle. The experiment uses a different principle than the underground xenon detectors. Inside ADMX, a small copper cavity is held in a powerful magnetic field, 8 Tesla, about 100,000 times stronger than the magnetic field of the Earth. If axions are streaming through the cavity, a small fraction of them can convert into ordinary photons inside the strong magnetic field, producing a faint microwave signal at a frequency set by the axion mass. The experiment tunes itself slowly across different frequencies, listening at each one for the signal of a converted axion. So far, it has not heard one. The experiment continues. There is no urgency. It has been listening, in its patient way, for a long time, and it will go on listening for as long as funding and human attention allow. There are also more exotic dark matter candidates that fall in between, neither point-like particles in the traditional sense, nor smooth fields. There are primordial black holes, hypothetical objects that might have formed in the first fraction of a second after the Big Bang, when patches of the very early universe were dense enough to collapse directly into black holes without ever passing through a star. If primordial black holes exist in the right mass range, they could account for the dark matter without invoking any new particles at all. They would simply be very old black holes, much older than the stars, drifting invisibly in the cosmic halos. The idea has been tested by looking for the microlensing signatures of such objects as they pass in front of distant stars. Many mass ranges have been ruled out by these searches. A few narrow windows remain open. The idea persists, sustained by occasional theoretical interest, and by the gradual accumulation of data from gravitational wave observatories like LIGO, which sees the mergers of black holes whose origins are not always clear. What unites the various dark matter candidates is the recognition that whatever dark matter is, it does not interact with light. It does not absorb light, does not emit light, and does not scatter light. It does not glow when it is hot, because perhaps it is never really hot in any familiar sense. It does not cool, because there is no light for it to shed. Ordinary matter clumps and collapses and forms stars because it can radiate away its heat, losing energy as photons, settling into denser and denser configurations. A gas cloud that is too hot to collapse can shed its heat as infrared radiation, slowly cool, and then collapse and form a star. Dark matter cannot do this. It is collisionless. It moves through itself as it moves through us, without friction, without resistance, without any of the slow exchanges that govern the world of atoms. This is one of the strangest things about dark matter, and one of the most important. It does not age in the way ordinary matter ages. Or rather, it does not change in the way ordinary matter changes. A cloud of hydrogen gas, left to itself in the universe, will slowly cool, will slowly clump, will slowly form a star, will slowly burn through its fuel, and will slowly die. The story of ordinary matter is a story of transformations, and most of those transformations involve the release or absorption of light. A halo of dark matter, left to itself, simply orbits. It moves in great slow currents under its own gravity, and it has been doing so for billions of years, and it will continue to do so for billions more. It has no internal life. It has no fuel to burn. It has, in a real sense, no story. And yet it shapes every story. Every galaxy we see exists because dark matter pulled the first gas together. Every star formed in a gravitational well that dark matter dug. Every spiral arm traces a pattern set by an invisible scaffolding that we cannot see. We are creatures of light and chemistry, and we live inside a structure built largely of something that has neither. The proof of dark matter at the deepest level came not just from rotation curves, but from a particular collision in deep space, a violent event that took place long ago and far away. The event is called the bullet cluster. The light from it has been traveling toward us for nearly 4 billion years. And when astronomers first turned their telescopes on it in the early 2000s, they found something they had been hoping for decades to see. The bullet cluster is what happens when two great clusters of galaxies pass through each other at high speed. The collision happened roughly 4 billion years ago. Each cluster contained hundreds of galaxies, a great mass of hot gas filling the space between them, and a vast halo of dark matter holding everything together. When the clusters met, the galaxies, being small and widely separated by cosmic standards, mostly passed through one another without colliding. The probability of any one galaxy hitting another in such a passage is small. The galaxies sailed on. The dark matter, being collisionless, also passed through, unimpeded, drifting on along its original trajectory. There was nothing for it to bump into, nothing to slow it, nothing to scatter it from its course. But the hot gas, being made of atoms that do interact, was slowed by friction. The gas of one cluster ran into the gas of the other, and the two clouds piled up in the middle, like cars in a slow accident, while the galaxies and the dark matter continued onward. By the time astronomers came to look at this system in the early 2000s, the result was unmistakable. The hot gas, which holds most of the ordinary matter in a cluster and shines brightly in X-rays, was sitting in the middle of the collision zone, drawn out into a characteristic bullet shape that gives the cluster its name. The Chandra X-ray Observatory, NASA's flagship high-energy telescope, photographed the gas in stunning detail. The galaxies were elsewhere, having sailed through, and the dark matter, traceable by the way its gravity bent the light of more distant galaxies behind the cluster, was elsewhere still, strongly offset from the gas, traveling with the galaxies, as if the two had passed cleanly through the wreckage. The technique used to map the dark matter is called weak gravitational lensing. The gravity of the cluster bends the light of distant background galaxies, slightly distorting their shapes, stretching them into faint, elongated patterns that point toward the gravitational center. By measuring these subtle distortions over many thousands of background galaxies, astronomers can reconstruct where the mass of the foreground cluster actually is. When they did this for the bullet cluster, the answer was clear. The mass was where the galaxies were, not where the gas was. The mass was, in other words, the dark matter, and it had passed through the collision without slowing down, while the gas had been caught in the middle. The map of the bullet cluster shows you a thing that is hard to deny. Where most of the matter is, no light shines. Where most of the visible matter is, very little gravity sits. The two have been pulled apart by the dynamics of the collision, and now they hover in their separate places. And the only way to explain this is that the great mass of the system is something that does not interact with itself, does not interact with the gas, does not interact with anything except through its own quiet gravity. The bullet cluster is often called a direct empirical proof of dark matter. It is as close to a smoking gun as cosmology has produced. The statistical significance of the separation, when first measured, was overwhelming. The probability of the result being a coincidence was estimated at less than 1 in a million billion. In the years since the bullet cluster was first studied, astronomers have found other examples of cluster collisions where the same separation appears. There is the train wreck cluster, also known as Abel 520, where the geometry is more complicated and the data harder to interpret, but where dark matter still seems to be misbehaving relative to the visible gas. There is the musket ball cluster. There are several others. Each one tells a similar story. Galaxies pass, dark matter passes, gas piles up. The mass is not where the gas is. The mass is where the dark matter is. And the dark matter, whatever it is, does not interact with itself in any way that the gas does. More recently, the James Webb Space Telescope has turned its larger mirror toward the bullet cluster, allowing astronomers to map the dark matter in even finer detail. by catching the faint, distorted shapes of more distant background galaxies than were previously visible. The picture has become more refined. The basic story remains the same. The bullet cluster, 20 years after it first made headlines, is still telling us that there is something out there, something massive, something that moves without friction, something that holds the galaxies together, but does not itself interact with anything we can detect. And yet, for all that proof, we still do not know what dark matter is. We know how it behaves. We know it is collisionless, or very nearly so. We know it is cold in the sense that its particles, whatever they are, move slowly compared to the speed of light. We know it does not interact with electromagnetism. We know it accounts for about a quarter of the total energy density of the universe. We know it has been here since the very early times, before the first atoms, before the first stars. But we have never held a piece of it. We have never made one, never trapped one, never seen one decay. It exerts its presence by gravity alone. Everything else is inference. The strangest thing about dark matter, perhaps, is how early it was. In the standard picture of cosmic history, dark matter was already organizing itself into structures, while ordinary matter was still trapped in a hot plasma, jostling with photons, unable to gather into anything more substantial than a slowly oscillating wave. For the first 400,000 years of the universe, ordinary matter and light were locked together in a single fluid, the photons pushing back against any clump that tried to form, the matter unable to settle. Whenever a region of ordinary matter began to gather under its own gravity, the photons trapped within it would push back, holding the matter at a kind of trembling equilibrium, allowing it to oscillate but never quite to collapse. But dark matter was not bound to the light. It could begin to fall together as soon as the universe was cool enough for gravity to act efficiently. Around the time the universe was about 50,000 years old, this moment is called matter-radiation equality, the time at which the density of matter in the universe first exceeded the density of radiation. Before that, the cosmos was radiation-dominated, and gravitational potential wells did not deepen efficiently. After that, the wells could grow. Dark matter began its slow work. In those quiet early millennia, while the rest of the cosmos remained smooth and bright and homogeneous, dark matter was already pulling itself into faint structures, long before there were stars, long before there were atoms in the modern sense, long before the universe became transparent. The seeds of all the galaxies that would ever exist were being laid down in invisible patterns. The patterns were small at first. They were imperceptible. They were tiny ripples in an otherwise smooth distribution. But they grew. They grew slowly because gravity is slow, but they grew steadily because gravity does not relent. When the ordinary matter finally cooled enough to decouple from the radiation and become atoms, when the universe became transparent for the first time, and the cosmic microwave background was released to travel outward forever, the ordinary matter fell into wells that dark matter had already dug. This happened at a temperature of about 3,000 degrees, when the universe was around 380,000 years old. The hot plasma cooled into neutral gas. The photons sailed free, and the gas, now no longer pushed back by trapped light, began at last to feel the gravitational landscape that had been waiting for it. The first structures of ordinary matter formed by falling into the structures of dark matter that had already taken shape. This is one of the deepest senses in which dark matter relates to time differently than ordinary matter does. Dark matter had a head start. It built the scaffolding while ordinary matter was still waiting for the lights to come on. Every galaxy in the observable universe sits in a dark matter halo that was older than the galaxy itself by hundreds of thousands of years. Every star is enclosed by a structure that began to form before stars were possible, and dark matter remembers in its slow way the patterns of those earliest fluctuations. The cosmic web that astronomers now map across the heavens, the filaments and walls and voids that organize the largest scale of the universe, is, at its deepest level, a map of dark matter. The galaxies are bright knots strung along filaments of dark matter that themselves trace the faint quantum ripples of the first instance of the cosmos. We are the embroidery on a fabric whose weave we cannot see. The fabric was there before we were. The fabric will be there after we are gone. In the cosmic web, there are filaments of dark matter that stretch for hundreds of millions of light years. There are voids between them, vast emptinesses where galaxies are scarce, and the dark matter density is low. There are nodes where many filaments meet, and in those nodes are the largest clusters of galaxies, weighed down by enormous dark matter halos. The geometry of the universe at its largest scales is set, almost entirely, by the geometry of the dark matter. Computer simulations of the cosmos, when they are made with only dark matter and gravity, reproduce the web that astronomers actually observe. Add the ordinary matter, with its more complicated chemistry and its messy hydrodynamics, and the simulations grow more detailed, but the basic structure does not change. The skeleton is dark. The flesh is ordinary. The bones determine the shape. It is worth pausing on the cosmic web for a while. The structure has been mapped in increasing detail by large galaxy surveys over the past several decades. The Sloan Digital Sky Survey, working from a small telescope in New Mexico, plotted the positions and redshifts of millions of galaxies. And when the data were assembled into three-dimensional maps, the pattern was unmistakable. The galaxies were not scattered evenly. They were strung along filaments, gathered in clusters at the nodes of those filaments, and absent from vast, empty regions in between. The voids were not quite empty, but they were nearly empty, with a galaxy density orders of magnitude lower than the dense regions. The whole structure looked, in computer renderings, like a great cosmic spider's web, or like the foam on a wave, or like the network of fissures in a piece of cracked ice. Simulations of dark matter alone, run on the largest supercomputers, produce exactly this pattern. The cosmologists who pioneered these simulations in the 1980s and 1990s were able to start from the small fluctuations seen in the cosmic microwave background and evolve them forward under gravity. And what emerged at the end of the simulation was the same web that the galaxy surveys had begun to map. The match was striking. It was, in itself, a strong piece of evidence for the basic dark matter picture. The structures we see are the structures that gravity, acting on dark matter, would produce. The agreement is detailed. It is quantitative. It works at every scale. Within the cosmic web, the filaments and walls have their own slow dynamics. Galaxies flow along the filaments toward the clusters. Smaller groups merge into larger groups. The cosmic web is not static. It is, on cosmic timescales, a slowly evolving organism, with mass flowing along its channels from the voids toward the dense knots. The Milky Way, our home galaxy, is a node of moderate size in a filament that connects it to the larger Virgo cluster, 50 million light-years away. Beyond Virgo, the filament extends to the great Laniakea supercluster, of which we are a small outlying member. Beyond Laniakea, the filaments extend to the Shapley supercluster and beyond, to scales so large that the imagination cannot easily picture them. We move along those currents, whether we know it or not. The Milky Way drifts toward a great gravitational attractor called the Shapley supercluster, a tide of dark matter and galaxies pulling us slowly across the cosmos at hundreds of kilometers per second. And the journey will take longer than the universe has existed so far. There is no hurry to it. Nothing about cosmic motion is ever hurried. The local group, our small neighborhood of galaxies, falls along filaments of dark matter that connect us to Virgo and beyond. The motions are smooth, vast, ancient. We are passengers on a flow that began before the Earth. Settle into that thought, if you like. The galaxy you live inside is being slowly drawn through the void, along currents older than any star, by a mass that no telescope has ever seen. Now we come to the question that gave this evening its title. The question of how dark matter relates to time. Whether dark matter, in some way, ages differently than the rest of us. There is no settled answer to this question. The honest answer is that physicists have several different ways of thinking about it, and the ways do not all agree, and none of them have been proven, and most of them are speculative in the best sense. That is, they are careful guesses, anchored in observation, but not yet confirmed. The first way of thinking about it is the simplest. Dark matter, as far as we can tell, exists in the same spacetime as everything else. It moves through the same expanding universe. It is subject to the same gravity, the same general relativity, the same flow of cosmic time. A clock made of dark matter, if such a thing could be built, would tick at the same rate as a clock made of ordinary matter sitting next to it. There is no separate dark time. Dark matter does not lag behind, does not leap ahead, does not experience any kind of altered duration. In this sense, dark matter ages exactly as we do. A second passes for the dark halo around our galaxy as it passes for the sun, and for the Earth, and for the small motions of a sleeper turning beneath a blanket. But there is another sense, and it is a deeper and stranger one. Dark matter, even if it experiences time at the same rate, does not change in the way other matter does. It does not undergo chemistry. It does not undergo nuclear fusion. It does not radiate. It does not, as far as we can tell, do anything except orbit and pull. Time passes for it, but very little happens. In the long history of the cosmos, the dark matter halo of the Milky Way has been almost exactly the same for billions of years. It has been reshuffled by mergers with smaller galaxies. It has been disturbed by passing satellites. It has been shaped, slowly, by the cumulative interactions of its many constituent particles, drawn together by their own gravity. But fundamentally, it remains what it has been since shortly after the universe was born. Ordinary matter, by contrast, has done a great deal in the same span of time. Stars have formed and died. Elements heavier than hydrogen have been forged in the cores of giants. Planets have cooled. Oceans have appeared. Living things have arisen and have begun, very slowly, to wonder about the dark. In this sense, dark matter is the still surface of the cosmos, and ordinary matter is the agitation on top. The asymmetry is worth dwelling on. Most of the activity we recognize as activity in this universe is the activity of the small visible fraction, the combustion of stars, the convection of planetary atmospheres, the slow chemistry of life, the rapid chemistry of nerves, the rustle of a leaf, the breath of an animal, the firing of a neuron. All of this is the work of ordinary matter, which makes up about a 20th of everything. The other 19/20ths is largely still. The dark energy spreads evenly and quietly. The dark matter orbits evenly and quietly. The universe, on average, is very calm. We live in a small unrest within a much larger stillness, and we sometimes mistake our unrest for the whole. There is something almost religious in the recognition. The activity we treasure, the activity we mean when we speak of life, is a vanishingly small exception in a universe that is, by mass, deeply at rest. The stars themselves, with all their fusion and their brightness, are a thin scattering on a vast, quiet background. The vast, quiet background is what the universe mostly is. There is yet another sense, more speculative, in which dark matter might relate to time in unusual ways. Some theoretical models propose that dark matter is not perfectly stable, that its particles, whatever they are, may have a finite lifetime, slowly decaying over cosmological timescales. In such models, the dark matter we observe today is not quite the dark matter that existed 13 billion years ago. A fraction has aged out of existence, transformed into lighter particles, into radiation, into something else. The remaining fraction is what we see. These models are called decaying dark matter models, and they are studied carefully because they have observable consequences. If dark matter were rapidly decaying, the structure of the cosmos would look different from what it does. There would be fewer small galaxies. There would be different patterns in the cosmic microwave background. The growth of the cosmic web would have been suppressed in characteristic ways, depending on how the decay products carried away the energy of the original particles. By looking at the universe today and asking what kinds of decay rates would have been consistent with what we see, astronomers can set limits on the lifetime of dark matter. Those limits are remarkable. The current best constraints suggest that if dark matter does decay, it must do so very slowly indeed. The lifetime of a dark matter particle, in the simplest such models, is bounded to be at least 100 billion years, and often much more. Some constraints push it beyond 100 quintillion years, which is to say, vastly longer than the current age of the universe. There is no observational evidence that dark matter is actually decaying. There is only the careful statement that if it is, the decay is very slow. The particles, if they have a finite life, live for stretches of time so long that the universe is, by comparison, brief. It is worth pausing on what that means. The dark matter that surrounds us, that holds the Milky Way together, that flows through our bodies as we sit here breathing slowly, is, in these models, very old. Older than the Earth, older than the Sun, older than the Milky Way itself. The individual particles, if particles are what they are, have been moving through the cosmos for nearly the entire age of time. And they will continue to do so for a stretch of time that we have no good way to imagine. They predate every star you have ever seen. They will outlast every star that ever forms. If a particle of dark matter could remember, it would remember the heat of the early universe, and the long cooling, and the slow gathering of the first structures, and the lighting of the first stars some hundreds of millions of years after the beginning, and the slow building of galaxy after galaxy, and the rise and fall of generations of stars, and the formation of planets, and the appearance of life on at least one of them, and the brief flicker of awareness that paused, one night, to wonder what the dark might be. None of this would have changed the particle. None of this would have made it any older, any wiser, any closer to ending. It would still be drifting, as it has always drifted, on the slow currents of the cosmic web. Of course, dark matter probably has no memory. Probably, it is not conscious in any way we would recognize, has no internal states, and has no experience of duration at all. It is a matter, in the simplest sense. It has mass, and it has motion, and it has gravity, and beyond those few things, it has very little. Whether it has an end, or whether it is truly eternal in some sense, we do not yet know. The decaying dark matter models come in several varieties. In some cases, the dark matter particle decays into lighter particles that move at nearly the speed of light, carrying away most of the original energy as a kind of dark radiation. In others, the decay is more gentle, with the particle splitting into a slightly lighter daughter particle and a small puff of energy, leaving most of the mass behind in a new form. The cosmological consequences differ. Rapid decay into relativistic products causes the universe to expand faster than it would have, and to grow structure more slowly. Slow decay with a heavy daughter causes only subtle modifications to the rotation curves of small galaxies. Observers compare the predictions of each model to the data, and the constraints tighten. Each year that passes without a sign of decay pushes the allowed lifetimes further out. The dark matter, if it dies at all, dies very slowly. There are reasons to be interested in decaying dark matter beyond simple curiosity. Some of the persistent puzzles of cosmology, such as the so-called Hubble tension between different measurements of the universe's expansion rate, have been proposed to be soluble by introducing a small fraction of decaying dark matter. If a portion of the dark matter has been quietly converting into radiation over cosmic time, it would have left subtle fingerprints on the expansion history of the universe. The idea has not been proven. It is, at present, one among many candidate explanations for the tension. But it keeps the question alive. There are also more speculative models in which the dark matter particle does not decay outright, but transforms slowly, shifting between different mass states, or interacting weakly with some hidden sector of physics in ways that change its observable properties over cosmic time. None of these models has been confirmed. None has been ruled out. The field is rich with possibilities, in part because there is so little observational guidance to constrain the imagination. Dark matter could be many things. It is presumably one specific thing. We do not yet know which. There is another idea, even stranger, which proposes that dark matter is not really made of particles in any familiar sense. It proposes that dark matter is a wave, a very slow, very gentle wave, oscillating across enormous stretches of space and time. This idea goes by several names: wave dark matter, fuzzy dark matter, ultralight dark matter. The basic notion is this: if dark matter is made of particles that are extraordinarily light, much lighter than any particle in the standard catalog, then it cannot behave as a cloud of distinct objects. It must behave instead as a quantum mechanical field smeared out over enormous distances. How light? In the most discussed versions of the theory, the dark matter particle has a mass of around 10 to the minus 22 electron volts. This is a number that does not mean much in itself, so let us translate it. The mass of an electron, which is one of the lightest familiar particles, is more than 100 billion times larger. The mass of a proton is larger still by another factor of 2,000. A fuzzy dark matter particle, if such a thing exists, is so feathery, so insubstantial as an individual object, that its quantum wavelength stretches across a kiloparsec or more. That is to say, the de Broglie wavelength of a single particle is roughly the size of a small galaxy. When you have particles whose individual wavelengths are larger than galaxies, you cannot treat them as particles. You must treat them as a wave. A single coherent wave filling the entire halo of a galaxy, oscillating at a frequency set by the particle mass. The wave has nodes and antinodes. It has constructive and destructive interference. It has a slow churn, a slow shimmer, a slow rhythm that depends on the mass of the particle and the size of the galaxy. And this is where time becomes strange. The frequency of the wave in the simplest fuzzy dark matter models is set by the particle mass through the relation that connects mass and energy in quantum mechanics. A particle of mass 10 to the minus 22 electron volts oscillates at a frequency of about 10 to the minus 22 seconds inverse, which is to say, very slowly. The oscillation period is on the order of a year for the lightest models, though the field varies stochastically on much longer timescales as well, and the precise figures depend on which version of the theory you adopt. The point is that the rhythm of fuzzy dark matter is slower than the orbital period of any planet, slower, in some senses, than the spin of a galaxy. The dark matter, if this picture is correct, is not a swarm of tiny moving things. It is one great slow note, sustained for a very long time. The halo of our galaxy is, in this view, an enormous standing wave, with humps and hollows of density that drift slowly and rearrange themselves over millions of years. The stars of the Milky Way move through this slowly shimmering field, feeling its gravity, mostly unaware of the deeper rhythm beneath them. There is a coherence time for such a wave, a span over which it holds its phase before becoming randomized. In the vicinity of the solar system, the coherence time for the fuzziest models is on the order of 1 million oscillations of the basic frequency. Beyond that, the field reorganizes itself, slowly, into a new pattern. The amplitude fluctuates stochastically. The direction of the field gradient drifts. Nothing about this is fast. Nothing about this happens on the timescale of a human life. But the field has a kind of slow weather, a slow turning, a slow forgetting of its own previous patterns. In this sense, fuzzy dark matter does have an internal rhythm, even if that rhythm is not what we would call aging. The wave persists. The shape of the wave evolves. The mathematical structure of fuzzy dark matter borrows from a phenomenon called Bose-Einstein condensation, in which large numbers of identical bosons settle into the same quantum state and behave collectively as a single coherent wave. In the laboratory, physicists have made small Bose-Einstein condensates from ultra-cold gases of certain elements. The condensates are usually only microscopic, but the dark matter halo of a galaxy in the fuzzy dark matter picture would be a Bose-Einstein condensate the size of a galaxy. A single quantum state, occupied by enormous numbers of identical particles, behaves as a single coherent field. The galaxy is, in this view, swimming in a cosmic-scale quantum object. There is an interesting consequence of fuzzy dark matter on small scales. Because the wave has a characteristic length scale set by the particle mass, fuzzy dark matter cannot clump on scales smaller than that wavelength. This means that the smallest galaxies, the so-called dwarf spheroidal galaxies, would have dark matter cores rather than sharp central cusps. The fuzzy wave cannot be compressed below a certain density. It smooths itself out at the smallest scales. Some observations of dwarf galaxies seem to favor this kind of chord structure, though the interpretation is contested. Other observations of certain very small clumps of dark matter have been used to constrain the fuzziness, ruling out the very lightest models. The field is active. The data are coming in. The picture is not yet settled. Fuzzy dark matter, like decaying dark matter, has not been proven. It has not been ruled out. The lightest versions are constrained by certain features of small galaxies, of dwarf spheroidal galaxies in particular, and by observations of the gas in the early universe. Some of these constraints make life difficult for the simplest fuzzy dark matter theories. But the broader idea that dark matter might be a coherent quantum field rather than a collection of point particles remains alive. The Axion dark matter experiment in Washington State listens patiently for the faint conversion of Axion dark matter into microwave photons inside a powerful magnetic field. It has not yet heard the signal. It may, one day, hear something. Or it may go on listening forever. There is something quietly beautiful about the picture. A universe whose hidden substance is a slow wave, oscillating across the dark, with a coherence time longer than a civilization. A halo that hums beneath the stars, in a key too low for any instrument to register. A patient field, filling the empty space, doing almost nothing, but doing it everywhere all the time, for as long as time has been. Sit with that for a while if you like. The universe is full of slow rhythms we cannot hear. The motion of the planets around the sun, on timescales of years and decades. The rotation of the galaxy occurs on a timescale of about 250 million years per turn. The slow precession of the Earth's axis, on a timescale of 26,000 years. The slow drift of the continents, on timescales of hundreds of millions of years. Each of these rhythms is too slow for our senses, but each of them is real, and each of them is happening around us all the time. If fuzzy dark matter is real, its slow rhythm joins this hidden chorus. The deep music of the universe is a music we mostly cannot perceive. We have spoken so far as if dark matter were certainly there, as if the inference were settled. And in truth, it very nearly is. The evidence for some kind of unseen mass is overwhelming, gathered from many independent sources, all pointing in the same direction. The cosmic microwave background, with its careful pattern of peaks and dips in the angular power spectrum, tells us how much dark matter the universe contains. The galaxy rotation curves tell us where the dark matter sits in galaxies. The bullet cluster tells us that the dark matter is not the same as the gas. The cosmic web, mapped by surveys of millions of galaxies, traces the dark matter at the largest scales. The lensing of distant quasars by intervening galaxy halos shows us the gravity of dark matter directly. Every line of evidence agrees. There is something there. But there is, in the corner of the field, a quiet alternative tradition, a small group of physicists who have wondered, for decades, whether the problem might not be missing matter at all. Whether the problem might instead be a flaw in our understanding of gravity itself. The chief alternative is called modified Newtonian dynamics, or MOND, proposed in 1983 by an Israeli physicist named Mordechai Milgram. Milgram looked at the flat rotation curves of galaxies that Rubin had measured, and he asked a different question than the dark matter advocates were asking. Rather than supposing that there must be invisible matter to account for the unexpected gravity, he wondered whether Newton's law of gravity might simply not apply at the very low accelerations that prevail at the edges of galaxies. In daily life and in the solar system, accelerations are relatively large. The Earth accelerates toward the Sun at nearly 6 millimeters per second. The Moon accelerates toward the Earth at a few millimeters per second. Even at the outer reaches of our solar system, accelerations are measured in fractions of a millimeter per second. But out at the edges of a galaxy, where stars orbit dimly at the periphery, the accelerations are vastly smaller. The characteristic acceleration scale that Milgram proposed, called a knot, is about 10 to the minus 10 meters per second. A number so small that it has no equivalent in any human experience. At accelerations below this scale, Milgram suggested, the gravitational pull might not follow Newton's inverse square law in the usual way. It might fall off more slowly than expected, producing flat rotation curves without requiring any dark matter at all. MOND, despite its odd appearance, has had real successes. It predicts, with a single parameter, the rotation curves of a wide range of galaxies, including some that are difficult for the dark matter picture to explain. It anticipates certain regularities, like the relationship between a galaxy's mass and its rotation speed, more naturally than the standard picture does. The Tully-Fisher relation, which links the luminosity of a spiral galaxy to its rotation speed by a power law, falls out of MOND almost automatically. While in the standard picture, it requires fine-tuning between visible and dark mass distributions, and MOND has the appealing quality of not requiring any new particles, any hidden sector, any invisible substance threading the cosmos. But MOND has problems too. It struggles, particularly, with galaxy clusters. At cluster scales, MOND alone cannot account for the observed dynamics. There is still missing mass, even in the modified theory. It struggles to explain the bullet cluster, where the gravitational and visible mass appear separated in space, a difficult observation for any theory that simply modifies gravity, because if gravity follows the visible matter, then the gravity should be where the visible matter is. The bullet cluster suggests that gravity is following something else, something not visible, and that something else is what we call dark matter. There have been attempts to extend MOND into a fully relativistic theory. The most well-known is called TVS, for tensor vector scalar gravity, proposed by the late Jacob Bekenstein in the early 2000s. TVS reproduces MOND on galactic scales and aims to handle gravitational lensing and cosmology consistently. It has had partial successes. It has had failures. The cosmic microwave background is hard for MOND-like theories to fit without including additional dark components. The growth of the structure is hard to reproduce. Most of the cosmology community, weighing the evidence, has come down decisively on the dark matter side. But a small, persistent tradition of MOND advocates continues to refine and extend the theory. The field has not settled. There are still open questions. Recent observations of the Milky Way's own rotation curve, made with data from the Gaia Space Telescope, have added to the conversation in new and unexpected ways. The story is not closed. This too is a feature of the night's subject, and not a flaw. The astronomy of dark matter is not a closed book. It is one of the great open questions of contemporary physics. Generations of researchers have devoted their working lives to it without a final resolution. The evidence is strong, but the identity remains elusive. The hidden mass is here, around us, in us, through us, and yet we cannot say what it is. There is, in many human philosophies, a comfort in not knowing. There is, in many religious traditions, a recognition that some things are too large to grasp, and that the proper response is not anxious searching, but quiet acceptance. Astronomy, too, has its long patience. We do not yet know what holds the galaxies together. We will perhaps know one day. Or we will perhaps spend many more centuries getting closer to an answer that never fully arrives. Either way, the universe does not require our understanding in order to continue. The dark matter has been here for 13 billion years. It can wait a few more. The history of physics is full of such patient questions. The nature of light, debated from the time of the ancient Greeks, was not settled until the 20th century. And even then, the answer was strange and partial. The atomic structure of matter, suspected by Democritus and others in antiquity, was not confirmed until the early 1900s. The existence of gravitational waves, predicted by Einstein in 1916, was not directly observed until 2015. The questions hang in the air for centuries sometimes, and then they are answered, and then there are new questions in their place. dark matter is currently one of the questions hanging in the air. The answer, when it comes, may take any of several forms. It may come in a single dramatic experiment. It may come piecewise, through many small results that gradually narrow the possibilities. It may come in a form that surprises us all. There is, in the writing of science, a particular tone that the long, patient questions invite. Not the urgent tone of the breakthrough, not the triumphant tone of the discovery, but the quiet tone of the open problem. The astronomers and physicists who work on dark matter spend their lives in this register. They write careful papers. They build careful experiments. They take careful data. They publish careful results. They move the limits, very slowly, in one direction or another. Their work is rarely featured in the popular press. The popular press wants the breakthrough. The careful work happens in the background, year after year, decade after decade, sometimes for a lifetime, without ever producing a single dramatic moment. And yet the field advances. Knowledge is added, possibilities are excluded, the mystery is approached very slowly from many sides. Let the thought rest there if it wishes to rest. What follows, in this last part of the journey, is the longest perspective. We will move out to the far future, to the last quiet stretches of cosmic time, and we will think for a while about what becomes of the dark matter in the long unwinding. The numbers we will use are large. They will not feel real. There is no way to make them feel real. The universe will outlast any attempt to picture it. The ultimate fate of the universe, in the picture most cosmologists currently accept, is something called heat death. The cosmic expansion continues, driven by dark energy, accelerating slowly as the eons pass. The galaxies drift apart. Eventually, in a few 100 billion years, every galaxy outside our own local group will have receded so far beyond our horizon that no signal could ever reach us from any of them. The night sky, for any observer of the very far future, will be much emptier than the one we know. Only the nearby galaxies, gravitationally bound to one another, will remain visible. In our own local group, gravity will pull the Milky Way and Andromeda together, and they will merge in roughly 4 to 5 billion years. The two great spirals, currently separated by about 2.5 million light years, and falling toward each other at about 100 kilometers per second, will eventually swing into one another's grasp. Their dark matter halos already overlap somewhat. As the galaxies approach, the halos will merge first, blurring into a single larger halo that pulls the visible disks ever closer. The disks themselves will pass through each other, perhaps several times, before settling into a single combined system. Most individual stars will not collide. The distances between stars, even in the dense inner regions of a galaxy, are so vast that a stellar collision during a galactic merger is a rare event, but the orbits of the stars will be reshuffled. The graceful spiral structure will dissolve into a featureless ellipsoid. The new galaxy, sometimes called Milkomeda in advance, will be vast, quiet, and gradually exhausting its supply of gas, with star formation slowing to a trickle. Other smaller galaxies will fall in afterward. The Triangulum galaxy, the third large member of the local group, will eventually be drawn into the merger. The Magellanic Clouds, already disrupted by the gravity of the Milky Way, will be torn apart and absorbed. The dwarf galaxies orbiting at the edge of the local group will, one by one, fall in. By the time the merger is complete, our small neighborhood of the cosmos will contain a single large elliptical galaxy and a few isolated survivors, all drifting through a darkness in which no other galaxy is visible. After that, the long fading. Star formation will continue here and there for a long time. The last main sequence stars will burn out in something like 100 trillion years. The smallest red dwarfs, the dimmest and longest-lived of the stars that fuse hydrogen, will be the last to go. Red dwarfs are extremely common. They burn for trillions of years on their tiny stores of fuel, but even they have finite supplies. Eventually, they too will exhaust their hydrogen, fade through helium-burning phases, and end as cold, dim cinders. After the last red dwarf has faded, the universe will consist mostly of stellar remnants. White dwarfs, slowly cooling, glow more and more faintly in the infrared, taking many billions of years to lose what little heat they have. Neutron stars, drifting in the dark. Black holes, eating what little remains. Brown dwarfs, never having shone, simply wait. The universe at this stage is called the degenerate era. It is dim. It is slow. The cosmic microwave background, redshifted by expansion, has long since faded to an even lower temperature than it has today. Activity in the universe has begun to wind down. What of the dark matter in this far future? The dark matter, in most models, simply continues. The halos persist, holding their dim contents, while the rest of the universe slows around them. If dark matter is stable on the timescales of these eras, then a halo will outlast the stars within it. The white dwarfs in the Milky Way halo will cool to invisibility, and the dark matter will still be there, drifting around an old core that has stopped shining. In some models, the dark matter halo is the last great structure left, persisting as the visible universe quietly thins. But if dark matter is not perfectly stable, then even the halos will slowly fade. A decaying dark matter halo, with a lifetime of, say, 10 to the 17th years, would noticeably erode over such timescales. By 10 to the 20th year, much of it would be gone. The cosmic web itself would begin to fray, as the great filaments of dark matter slowly returned their mass to whatever lighter products they decay into. In such a picture, even the deepest scaffolding of the universe is impermanent. Nothing endures forever. The structure that built the galaxies will, eventually, also vanish. Beyond 100 quintillion years, even the supermassive black holes at the centers of galaxies will begin to evaporate, very slowly, through Hawking radiation. The largest of them, the black holes at the cores of the most massive galaxies, will take perhaps 10 to 100 years to fully evaporate. This is a number so vast that the writing of it strains language. The age of the universe today is about 10 to the 10th years, or roughly 13.5 billion years. 10 to the 100th years is 1 followed by 100 zeros. There is no useful way to imagine it. The universe in those years will be inconceivably cold, inconceivably empty, with photons and electrons and positrons drifting through a space so dilute that any particle is unlikely to encounter another within the lifetime of the cosmos, as we know it. In some far future, the last black hole evaporates. After that, the universe enters what is called the Dark Era, a period of essentially no activity, in which the cosmos consists chiefly of a thin gas of low-energy photons and a few stray particles, drifting through a space that is approaching absolute zero. There is nothing left to happen. There are no clocks because there are no events for clocks to count. Time still flows in a mathematical sense, but there is nothing for it to flow through. It is worth saying, gently, that all of these timescales are speculative. The very far future of the universe depends on properties of physics that we have not yet measured. The stability of the proton, the behavior of dark energy at very late times, the exact nature of dark matter, the possibility of vacuum decay or other phase transitions. Any of these could change the story dramatically. We do not know if the universe ends in cold quiet or in some sudden violence we cannot anticipate. We know only what the simplest extrapolation suggests, and the simplest extrapolation is the long fade. What we know for certain is much shorter and much closer. The sun will go on shining for another 5 billion years or so. The Earth will be habitable in some form for perhaps another billion. The galaxies will go on turning for many ages yet. The dark matter, whatever it is, will continue to do what dark matter does, which is mostly nothing. The halo will hum on beneath the stars in its slow, patient way. There is a quietness in such timescales that is hard to put into words. The numbers themselves are too large to grasp. 1 trillion years, 100 trillion years, 100 quintillion years, 10 to the 100th years. Each number is followed by another that dwarfs it, and there is no place to plant the imagination, no scale on which any of this becomes intuitive. The mind slides off the surface of these numbers. It is fine that the mind slides off. The numbers were not made for human grasping. They were made by the universe at its own slow pace, and they do not require our participation in order to mean what they mean. And the stars will continue quietly doing what stars do for ages too long to feel. The dark matter will hold them. The dark matter has always held them. There is a thought that comes back in this kind of meditation that may be worth returning to. It is the thought that the great mass of the universe is something patient. Ordinary matter is restless. It burns, it cools, it builds, it falls apart. Living matter is the most restless of all, always doing something, always needing something, always changing. But dark matter does not burn, does not need, does not change in any urgent way. The bulk of the universe, by mass, is at rest in some deeper sense. It moves under gravity, but it does not seek, does not consume, does not strive. It simply is. If there is a comfort in cosmology, it is sometimes this: that most of what is real in the universe is calm, that the noise and motion of the visible world is the exception, not the rule, that the great majority of the cosmos is quiet and slow and content to drift. We do not know what dark matter is. We have many guesses, and the guesses are clever, and the experiments are patient. And someday, perhaps, one of the experiments will find what it is looking for. There will be a faint signal in a deep mine on a quiet morning, and the long search will end. Or there will not be such a signal, and the search will continue, decade after decade, generation after generation. Either is acceptable to the universe. The dark matter does not care whether we find it. It is there in any case. Outside our windows, the night extends. The Milky Way wheels overhead, holding its hundreds of billions of stars in its slow grip. Beyond the visible disk, much further out, the dark halo extends, far thinner than the disk, but far more massive. It reaches almost to the edge of the gravitational influence of the galaxy, hundreds of thousands of light years from where we sit. It moves around us as we sit here. It has always moved around us. The sun has been drifting through it for 4.5 billion years, and the Earth and the Moon have come along for the ride. None of us has ever felt it, but it has been holding us all along. A halo of dark matter passes through our bodies, and through our chairs, and through the room we are in, and through the city and the country and the continent. It does not nudge anything. It does not interact. It is simply there, woven into the same space where we sit. There is no special place where dark matter is, and we are not. There is one universe, and dark matter fills it, quietly, alongside everything else. The density of dark matter near the sun is small. Estimates place it at about 1/3 of a billionth of a gram per cubic centimeter, give or take, depending on how you measure it. Spread across the volume of a human body, that amounts to a tiny mass, far too small to feel. The dark matter in this room weighs less than a flake of dust, but spread across the volume of the Milky Way, the same density adds up to nearly 1 trillion solar masses, which is roughly 6 times the mass of all the visible stars in the galaxy combined. Density matters less than volume in the end. The dark matter is sparse but pervasive. It is everywhere, and so it is much. Some part of the dark matter around us has been here since long before the sun was born. It was here that the gas cloud that became the sun was first beginning to gather. It was here when the earth was forming. It was here when the oceans appeared. It was here that the first cell divided. It was here when the dinosaurs walked. It was here that the first human looked up at the sky and wondered. It will be here long after all human wondering has ended. It is the most patient thing we know. There is no urgency to dark matter. There is no urgency to any of this. The universe does not hurry. The universe has never hurried. It has done its work over 13.5 billion years, and it has another vast stretch of time ahead, and there has never been any need to rush. The thoughts can drift now if they wish. There is no need to follow each idea to its conclusion. The conclusions are themselves uncertain. The shape of the night is enough. Somewhere, in a deep mine, a tank of liquid xenon waits. Somewhere in a cold laboratory, a copper cavity tunes itself to the possible frequency of an axion. Somewhere, in a quiet observatory, an astronomer is sitting at a desk with the rotation curve of a galaxy on the screen. And she is wondering, as Vera Rubin wondered, what holds all of this together. The work goes on. It will go on for many more years. There is no particular hurry. The galaxies turn. The dark halos hold. The cosmic web stretches, patient and slow, across the deep. There is more of it than there is of us, by a great margin. We are the small, bright pattern on a vaster, darker cloth. There is a long tradition in human thought of imagining the night sky as full of meaning. The constellations were named for heroes, animals, and gods. The planets were assigned to days of the week. The Milky Way was, in many cultures, a road traveled by spirits, or a river, or the flowing breast of a goddess. We have always wanted the sky to speak to us. We have always wanted the dark to mean something. The dark matter does not speak. It has no story it is trying to tell. It is not symbolic. It is just there. It pulls, and the things it pulls move, and from the moving we infer the pulling. Beyond that, there is nothing it asks of us. It does not require our attention. It does not require our names for its parts. It does not even, in any meaningful sense, know that we exist. The relationship is one-sided. We notice the dark matter in our slow way with our slow instruments. The dark matter, if it could be said to notice anything, does not notice us at all. This too can be a comfort. We sometimes feel in our restless waking lives that the universe is watching, that the cosmos has opinions about what we do. The dark matter is a reminder that most of the universe is utterly uninterested. There is no judgment in the dark halo around the galaxy. There is no opinion in the cosmic web. There is only the slow turning of mass under gravity, the same now as it was when the universe was young, the same as it will be when the universe is old. We are very small. The dark matter is very large. Between us and it, there is no quarrel, no contest, no expectation. We share the same space briefly for the duration of one human life, and then we are gone, and the dark matter continues, unchanged, unmarked, unhurried. The Milky Way, our home galaxy, is wrapped in a halo of dark matter that extends, by some estimates, to 1 million light-years or more from the galactic center. The bright disk of stars that we recognize as the Milky Way is only 30,000 parsecs across. roughly 100,000 light-years. The dark halo is many times larger than the visible galaxy. The galaxy we see is a small bright nucleus inside a much vaster dark egg. The same is true of Andromeda. The same is true of every spiral galaxy that has been carefully studied. The visible part is always the smaller part. The dark part is always the largest. This is, in some ways, the lesson of cosmology in a single sentence. The visible part is always the smaller part. What we can see is never the whole. There is, in every galaxy, a hidden mass that outweighs the bright stars by an order of magnitude or more. There is, in every cluster, a hidden mass that outweighs the visible gas by a factor of 5 or 6. There is, in the universe as a whole, a hidden mass that outweighs all the ordinary matter put together. The universe we see is a partial picture. The universe we know about is a much fuller one. The universe that actually exists is, presumably, fuller still, in ways we have not yet thought to imagine. Astronomy, more than most sciences, teaches a particular kind of humility. There is always more out there than we have seen. There are always patterns at scales we have not yet measured. There are always objects of types we have not yet classified. The history of the field, spanning centuries, is a long story of expansion. The world was bigger than ancient peoples thought. The solar system was bigger than the medieval astronomers thought. The galaxy was bigger than the early 20th century astronomers thought. The universe was bigger than Edwin Hubble thought when he first established that it was made of many galaxies. And the universe is, by mass, much fuller than even the cosmologists of the mid-20th century thought, because most of the mass is dark, and most of the mass is something we have not yet identified. The lesson is that the universe is generous with surprises. The lesson is also that the surprises tend, over time, to fit together. The dark matter that Zwicky inferred in 1933 turned out to be related to the dark matter that Rubin inferred in 1970, which turned out to be related to the dark matter that the Bullet cluster revealed in 2006, which turned out to be related to the dark matter that the Planck satellite measured in 2013. The story has held together even as each new piece of evidence has been added. The pieces have fit. The picture has grown more coherent, not less. We do not yet know what dark matter is, but we know more than we did, and what we know is consistent, and the consistency is itself a kind of progress. There is nothing here that needs to be remembered. There is nothing that needs to be solved tonight. The dark matter has been here all the while, and it will be here in the morning, and it does not require anyone to be awake in order to continue. It has continued through every night of every life. It has continued through ages when no living thing was awake anywhere in the cosmos. It continues now, even as the breath slows, even as the room grows quieter, even as the small lights of consciousness dim toward sleep. The mind can wander where it wishes. The thoughts can come apart like the ends of long sentences drifting into silence. There is no part of the universe that requires the mind to follow it. The mind can stop following. The universe will continue without it. In the morning, the stars will still be there, hidden by the light of day, held by halos we cannot see. The Milky Way will still be turning. The galaxies of the local group will still be drifting toward each other on currents that began before the sun was born. There is no hurry to the long story. There never has been. The universe is mostly quiet. The universe is mostly dark. The universe is mostly something we do not yet understand. And that, perhaps, is fine. The dark has been here for a long time. It is not going anywhere. It is the deeper part of the night, the part beneath the stars, the the part that holds them in place. It does not need to be named to be real. It does not need to be measured to be true. It has been there since the universe was new, and it has done its quiet work without any witness, and it will go on doing its quiet work long after any witness has gone. There is something restful in that thought. Not every truth in the universe requires us. Not every pattern needs an observer. The galaxies do not turn for us. The dark halos do not hold for us. The cosmic web does not stretch for our admiration. These things exist, and they would exist whether or not we had ever been here to notice. Our noticing is a small, late event in a very long story. The story does not depend on us. This is a comforting thought in its way. We do not have to be present for the universe to be real. We do not have to be awake for the dark matter to keep doing what it does. We can sleep, and the cosmic web will hold. We can sleep, and the dark halo of the Milky Way will continue its slow turning around us. We can sleep, and somewhere in a deep mine, a detector will continue to wait for a signal that may or may not come tonight. There is no need for vigilance. There is no need for attention. The universe is taking care of itself in its old, slow way, and it has been doing so for a very long time, and it will continue to do so for a very long time more. Consider, for a moment, the journey that a single particle of dark matter, if such a thing exists, might have made by now. It came into being in the very early universe, perhaps within the first second after the Big Bang. It drifted in the hot, dense plasma of those first moments, feeling the pull of every other particle, but not interacting with light. As the universe cooled and expanded, it joined with countless others of its kind in the slow gathering of the first faint structures. By the time the universe became transparent, 380,000 years in, the particle was already part of a growing overdensity, an early seed of what would one day be a galaxy. For hundreds of millions of years, the particle moved within that growing structure, feeling the gravity tighten around it as more and more dark matter fell in. The first stars eventually lit up, somewhere in or near the structure. Galaxies formed. The galaxy that would become the Milky Way coalesced. The particle has been orbiting within that galaxy, in its slow, patient way, for nearly 13 billion years. Through all of that, the particle has not aged in any way we would recognize. It has not lost energy. It has not radiated. It has not transformed into anything else. It has simply moved under gravity in the gravitational landscape of the universe, and it will continue to move in the same way for as long as it exists. If it has a finite lifetime, that lifetime is so long that the current age of the universe is, by comparison, a moment. If it has no finite lifetime, then it will simply continue indefinitely, drifting in the long dark, doing what it has always done. There is something beautiful in this kind of persistence. The dark matter does not seek meaning. It does not search for explanations. It does not yearn for completion or for an ending. It simply continues. It is, in some sense, the most patient kind of being there is, if being is the right word for something so quiet and so unchanging. The dark matter does not need to do anything. It does not need to mean anything. It is enough to exist. We can take some comfort from this. Not everything that exists has to be useful. Not everything that exists has to have a purpose. The vast majority of the universe, by mass, exists without purpose in the human sense. It simply is. And out of that vast, simple being, somehow, the conditions arose for the brief unrest of life, for the small, flickering complexity of consciousness, for the kind of slow wondering that fills a quiet evening when the rest of the world is going to sleep. The dark matter holds the galaxies. The galaxies hold the stars. The stars hold the planets. The planets hold, occasionally, the rare, delicate accidents of life. And life, on at least one of those planets, sometimes pauses late at night to look up at the sky and wonder. The wondering is brief. The dark matter is long. The dark matter will continue when the wandering has stopped. The dark matter has been holding everything together since long before there was anyone to ask what was holding everything together. The answer to the question, if there is an answer, has been waiting all along patiently in the dark. The stars continue quietly as they have for billions of years. The dark halos hold. There is nothing to do here. There is nowhere to be. The universe will still be turning when you wake.